Good day to each and everyone. We are the second group and we are going to report Chapter 2 in our subject, the Introduction to the Linear Programming. I am Rashid Sendad and with me is Angelica Guiapal and Macatanog. Let's begin. Linear programming is a problem-solving technique that was created to assist managers in making their decisions. Linear programming leads a company to a choice on how to maximize or minimize certain quantity in the company. For example, if a marketing manager wishes to identify the optimum way to divide a set advertising budget across different advertising media such as radio, television, newspaper, and magazine, and at the same time would maximize the advertising effectiveness of the firm, then he may use the linear programming to achieve this goal. However, problems like this have a feature known as restriction or constraints, which limit how far the goal may be pursued. In the problem given, a set of advertising budget and the availability of numerous media constrain the marketing manager's media selection decision. Let me give you a story that relates to maximizing a quantity using linear programming. Once, there was a company named PAR Incorporated who was a small golf equipment and supply company whose management has decided to enter the medium and high-priced golf bag in market. PAR's distributor has caught the interest of the new product line who was committed to purchase all the golf bags produced by PAR over the next 3 months. After a comprehensive examination of the procedures required in manufacturing a golf bag, the management of the company concluded that each golf bag, for it to be manufactured, requires the following activities. Number 1, cutting and dyeing of the materials. Number 2, sewing. Number 3, finishing, inserting umbrella holders, club separators, etc. And number 4, inspection and packaging. According to the Director of Manufacturing, if the company produces a medium price standard model, each bag will require 7/10 hour in the cutting and dyeing department, 1/2 hour in the sewing department, 1 hour in the finishing department, and 1/10 hour in the inspection and packaging department. On the other hand, the more expensive deluxe model of bags in cutting and dyeing will take 1 hour, sewing will take 5/6 of an hour, finishing will take 2/3 of an hour, and inspection and packaging will take 1/4 of an hour. This table summarizes the production information. PAR's production is constrained or restricted by the fact that each department has a certain amount of hours available. The Director of Manufacturing anticipates that during the following 3 months, 630 hours will be available for cutting and dyeing, 600 hours will be available for sewing, 708 hours will be available for finishing, and 135 hours will be available for inspection and packaging based on the departmental workload estimations. The accounting department examined the production data, allocated all relevant variable costs, and calculated pricing for both bags that result in the profit contribution of $10 per every standard bag produced and $9 for every deluxe bags produced. Now, let's create a mathematical model for the PAR Incorporated problem that can be utilized to figure out how many standard bags and deluxe bags can they make in order to optimize the overall profit contribution.
Formulation, also known as a modeling, is the process of converting a problem's verbal statement into a mathematical statement. Modeling is an art can be only mastered through practice and experience. Even though each problem has some distinguishing characteristics, the majority of problems share some characteristics. As a result, some general guidelines for model formulation, particularly for the beginners, can be useful. We will demonstrate these broad guidelines by creating a mathematical model of the problem. It is not easy to understand problem to introduce linear programming. More complex problems, for the other hand, will necessitate a lot of thoughts in order to select the components that must be included. The goal is to maximize the entire profit contribution. Our constraints limit the amounts of regular bags and deluxe bags. The many produced according to the number of hours of manufacturing time available. Constraint number 1. The number of hours spent cutting and dyeing must be lower than or equal to the number of hours available, both cutting and dyeing. Constraint number 2. The total number of hours spent sewing must be fewer than or equal than total of the hour available. Constraint 3. The number of hours required for finishing must be lower than or equal to the number of hours available to finishing. Constraint number 4. The number of hours to use for inspection and packaging must be lower than or equal to the number of hours available for inspection and packing. Make a list of the variables that will be used to take a decision. The number of basic bags produced, a number of the deluxe bags produced, and the two comparable input let. S. Number of the standard bags. D. Number of deluxe bags. Profit contribution comes from two sources. 1. Profit contribution from S standard bags, and 2. Profit contribution from the D deluxe bags. It pays 10 per standard bags. The business can be earned 10S if the S standard bags are made. Therefore, if PAR earns 9 for the each deluxe bags produced, company will earn 9 if the deluxe bags are produced as a result. We refer to the 10S and 9S and the objective function, since the goal maximized to the profit contribution is a function of the decision variable S and D. We should write PAR's goal as follows using max as an abbreviation for maximize. Term of the decision variable constraint 1. PAR will use 710 hours cutting and dyeing time for every standard bag it produces. As a result, the total number of hours of cutting and dyeing time required in the production of S standard bags is 710S. Moreover, because each deluxe bag takes 1 hour to cut the dye, the production of D deluxe bags will take 1D. Hour of cutting and dyeing time. As a result, the total cutting and dyeing time for the production of S standard bags and D deluxe bags is calculated by using the following. Strand 2. We can see from table 2.1 and every ordinary bag created will take 12 hours to sew, and every deluxe bag should take 56 hours to sew, due to the fact that 600 hours of manufacturing time are available. Constraint 3. Very standard bag manufactured will be about 1 hour to finish, but then every luxury bag will take 4 hours to finish, will 708 hours to complete the task. It follows that. Constraint 4. Every regular bag produced will take 110 hours to inspect the package, while every minimum bag will be take 14 hours to inspect and the package, because there are 135 hours to inspection and the packaging time available. Because every point SD corresponds to the possible solution, every point on the paragraph is called solution point. The solution point where S0 and D0 is referred to as the original, because S and D must be non-negative. The paragraph figure 2.1 only displays solution where S0 and D0. Earlier, we saw that inequality responding the cutting and dyeing constraint. Our task now is discover a product mix combination of S and D meets of the all restrictions, while also yielding a value of the objective function that is greater than or equal to the other possible solution. We will have found the best solution to the problem once this value have been calculated. A linear programming paradigm or the linear program is used to solve the PAR issue mathematically linear program. The problem has the objective constraints that, as we said earlier, are common properties of all linear programs, but is the special models that makes a linear program. The special feature that makes a linear program are goal to function, as well as all constraints function are all linear function of the decision variable, which make it a linear program. As a result, this problem mathematical description is known as a linear program. The term linear program refers to technique has nothing to do with computer programming. The term His refers to the deciding of the path of the action, where the mathematical model of the problem contains the linear functions. Linear programming is used to choose a course of action. A graphic solution is approach can be used to solve a linear programming issues with only two choice variables. Let's start with the graphic solution technique by creating a graph, then show the problem as alternative solution S and D values.
Hello, this is Angelica Guiapal reporting about the graphical solution procedure. A linear programming including the two value can be addressed utilizing a graphical solution procedure. Allow me to start the graphical arrangement technique by fostering a graph that shows the potential arrangement of S and D value. The graph displayed at the figure 2.1 will have the upside of S as the flat half while the D on the upward pivot. Any point of the graph can be recognized by S and D qualities, which shows a situation of point of the graph that can be identified along the level of vertical and horizontal, individually on the grounds that each place of S and D relates for conceivable arrangement. Each mark of the graph is called solution point. The solution point where S is equal to 0 and D is equal to 0 is alluded to as beginning. Since S and D should be non-negative, the graph that shows in the figure where S is greater than or equal to 0 and D is also greater than or equal to 0. To track down a subsequent point fulfilling this condition, we set D is equal to 0 and tackle the S. As you can see in the given graph below, where the solution point of the standard of bugs pointed compared to the number of the logs backs.
The availability of graph lines representing the constraints and the linear program's objective function is an essential feature of the graphical method. We utilize the method of finding any two locations that satisfy the equation and then drawing a line across them to graph the equation of a line. The 2 points were readily determined for the PAR incorporated constraints by first setting S is equals to 0 and then solving the constraint equation for D. Then we set D is equals to 0 and solve for S. For the cutting and dyeing constraint line, we have an equation 7/10 S plus 1D is equals to 630. This procedure identified the 2 points S is equals to 0, D is equals to 630, and S is equals to 900, D is equals to 0. The cutting and dyeing constraint line was then graphed by drawing a line through these 2 points. In two-variable linear programming, all constraints and objective function lines may be graphed if 2 points on the line can be identified. Finding the 2 points on the line, however, is not always as simple as it appears in the PAR incorporated scenario. The graphical solution approach, as we've seen, is a technique for addressing two-variable linear programming problems like the PAR incorporated problem. The steps of the graphical solution process for a maximization problem are summarized as follows. 1. Make a graph of all the possible solutions to each constraint. 2. Find the solutions that meet all of the constraints and at the same time to determine the feasible region. Number 3. Draw an objective function line that depicts the values of the choice variables that result in a given objective function value. Number 4. Continue moving parallel objective function lines toward bigger objective function values until the line reaches the edge of the feasible region. Number 5. An optimal solution is one that is feasible on the objective function line with the highest value.
Lack variables, also known as IDLE, capacity variable, are introduced to the formulation of the linear programming problem to indicate slug's capacity because unused capacity does not contribute to profit. Slack's variable have two zero coefficient. The mathematical model was complete of the additional of slack variable labeled S1, S2, S3, and S4. As a result, the complete solution informed management that the production of 540 standard bags and 252 deluxe bags will consume all available, cutting in dyeing time 630 hours, finishing time 708 hours, while 648, 120 hours of sewing the time and 135 and 117, 18 hours of inspection that packaging the time will go unused. Extreme points. The optimal solo tuition every point SD corresponds to possible solution. Every point and graph in called is solution point. The solution point where S0 and D0 is referred as the origin. Because S and D must be negative, the paragraph is a figure 2.1 only displays solution where S0 and D0 earlier. We saw that the equality repress. What effect does this change in the objective function of on the far? Problem's optimal solution. The graphic solution of this new problem with the altered objective function is shown in figure 2.12. It worth nothing that variable region remains unchanged if the limits remain unchanged. The profit lines, on the other hand, have been changed to reflect a new project function. We discovered that ideal solution by shifting the profit line in a parallel fashion towards greater profit values as shown at the figure 2.12. At this moment, the decision variable values.
Computer programs intended to take care of direct programming issues are currently generally accessible. The greater part of the organization approach these programs after the brief time of acquaintance with the particular components of the bundle. Clients can take care of the direct programming issues with not many hardships, including a large number of a factor and a huge number of limitations are currently regularly settled with the bundles. The vast majority of direct projects that can be addressed. So more recently, with the virtual explosion of software for personal computers, a large number of user computer programs that can be solved, linear programs became available. These programs, developed by academicians and small software of companies, are almost easy to use. Most of these programs are designed just to solve the linear programs with a few hundred of variables, but some can be used to solve the problems involving thousands of variables and constraints. For the problem interpretation, let's investigate all the more intently for the computer solution arrangement. The ideal answer for this will give the benefits of $7,668 straightforwardly underneath the target work esteem. After we track down the choice factors of ideal arrangement, recently we had S is equals to 540 for the standard stack and D is equal to 252 to choice pack as the ideal creation of its amount. Review that standard had 4 not exactly equivalent for hour to requirements to comparing to the hours accessible in every 4 creation offices. The data displayed in the leeway of surplus section offers the benefits of leeway factors of every offices. The data summary gave of the number of requirements, the number of the leeway about, and the number of the leeway is about the creation of the standard incorporated. From this yield, we see the limiting of requirements, the cutting and dyeing, and the completing imperatives have a zero leeway at the ideal arrangement. The sewing office has 120 hours slack unused of limit. It tends to be utilized to decide how the changes in the info about the sway of the ideal arrangement.
Another story that I'll tell you about is one that has something to do with minimization problem. M&D Chemicals is a company that manufactures 2 items that are supplied as raw ingredients to firms that make bath soaps and laundry detergents. M&D's management stipulated that the combined output for items A and B must be reached at least 350 gallons based on an estimate of existing inventory levels and projected demand for the next month. A large customer's purchase for 125 gallons of product A must also be fulfilled separately. Processing time for product A is 2 hours per gallon, whereas processing time for product B is 1 hour per gallon. 600 hours of processing time are available for the next month. M&D's goal is to meet these objectives at the lowest possible overall cost of manufacturing. Product A costs $2 per gallon to produce, whereas product B costs $3 per gallon. We will write the M&D's chemical problem as a linear program to determine the lowest cost manufacturing plan. We start by defining the decision variables and the objective function for the problem, similar to how we did for the PAR Incorporated problem. Let A represent the number of gallons for product A and B represent the number of gallons of product B. The objective function that corresponds to the minimization of the total production cost may be expressed as min 2A plus 3B with production cost of $2 per gallon for product A and $3 gallon for product B. Consider the limitations that has been imposed on the M&D chemicals issue. We know A must be at least 125 gallons to meet the big customer's demand for 125 gallons of product A. As a result, we put 1A is greater than or equal to 125 as a constraint. We may put the restriction 1A plus 1B is greater than or equal to 350 for the combined production of both goods, which must amount at least 350 gallons. And finally, we add the restriction 2A plus 1B is less than or equal to 600 to the possible processing time limit of 600 hours. We get the following linear program for the M&D chemicals issue after adding the non-negativity requirement. A, B is greater than or equal to 0. The graphical solution technique may be utilized to discover the best production quantities because the linear programming model only has 2 decision variables. As with the PAR issue, the graphical solution technique for this problem needs us to first graph the constraint lines in order to locate the feasible region. The feasible solutions for each constraint may be found by graphing each constraint line individually and then verifying points on each side of the constraint line. The feasible region depicted in this graph is obtained by merging the viable solutions for each constraint on the same graph. We now draw the objective function line corresponding to a certain total cost value to identify the lowest cost option. We might begin by sketching the line 2A plus 3B is equals to 1,000, for example. This graph depicts this line. Clearly, some places inside the feasible region would cost 1,200 in total. We shift the goal function line to the lower left to discover the value of A and B that result in reduced total cost. If we move it any farther, we will be completely outside the feasible region. At the extreme points, A is equals to 250 and B is equals to 100, the objective function line 2A plus 3B is equals to 800 intersects the feasible region. With an objective function value of 800, these extreme points gives the lowest cost option. The total production restriction and the processing time constraint are both binding. The optimal solution occurs at an extreme point in the feasible area, just as it does in any linear programming problem. The following are the steps in the graphical solution process for a minimization problem. Number 1. Make a graph of all the possible solutions to each constraint. Number 2. Find the solution that meet all the restrictions and at the same time to determine the feasible region. Number 3. Draw an objective function line that depicts the values of the decision variables that result in the given objective function value. Number 4. Continue moving parallel object function lines towards lower objective function values until the line reaches the edge of the feasible region. And number 5. 5, an optimal solution is any possible solution of the objective function line with the least value. The value of the surplus or slack variables S1 is equals to 125, S2 is 0, and S3 is 0.
The MND chemicals problem has been solved by computer. Figure 2.17 depicts the best solution to MND. The best minimum cost solution produces an object function value of 800. According to the computer report, the decision variable suggests the lowest cost solution in 250 gallons of product A and 100 gallons of product B.
In these special cases, the other ideal arrangement is likewise called as an other optima, which is the straight or whole number programming issues has more than one ideal arrangement. Commonly, and the ideal arrangement is an answer for an issue which fulfills the arrangement of limitations of the issue and the target work, which is to augment or limit. On the conversation of the graphical strategy, we realize that the ideal arrangement can be found at the Australia's mark of plausible district. Presently, let us consider the uncommon case where an ideal target work line matches with one of the limiting idea or the limitation lines of the limit of attainable district. We will see that the present circumstance confirms the instance of option ideal arrangement. In such cases, more than one arrangement offers the ideal benefits for the goal work. To show the instance of elective target arrangement, we return to the standard issue. Anyway, let's expect that the benefits for the standard SAC has been diminished as $6.30. The overhauled target capacities become 6.30S plus 9D. In the graphical arrangement of this issue, as I shared the method before, that the ideal arrangement actually happened at the extreme point. For the given graph below, for the Australian point, as we can see, the standard is equivalent of 300 while the deluxe is 420. I'm sorry. Also, the Australia's point 3, that we can see that the standard is equivalent of 540 while the deluxe is 252. A straight programming issue with the options ideal arrangement is for the most part great circumstances for the administrator or choice chip. It implies that the few blend of choice factors and ideal that the supervisor can choose the best of ideal arrangement. Sadly, to determine whether an issue has an ideal elective arrangement is certainly not a straightforward matter. Now let's proceed on infeasibility. When infeasibility means no answer for the direct programming issue, fulfilled every one of the limitations including the non-negativity condition. Graphically, infeasibility implies that a possible area doesn't exist. That is, no focuses of all fulfill in all the constraints and non-negativity condition at the same time. To show the present circumstance, suppose that the administrator or administration determined that somewhere around 500 standard packs, at least the 360 of the deluxe sacks should be made.
A maximization linear programming problem's solution is unbounded if the solution's value can be made endlessly big without breaking any of the restrictions. A minimization problem's solution is unbounded if the value can be made infinitely small without violating any of the requirements. This state is known as managerial utopia. For example, if this state occurs in a profit maximization issue, the manager will be able to make an endless profit. The presence of an unbounded solution in linear programming models of actual problems, on the other hand, indicates that the problem has been incorrectly stated. Profits cannot be increased endlessly, as we all know. As a result, if a profit maximization issue has an unlimited solution, the mathematical model does not adequately describe the real-world problem. Typically, a constraint has been neglected accidentally throughout the problem formulation process.
General linear programming notation. We demonstrate how to develop linear programming models for the M&D chemical problem in this chapter. We started to identifying with choice variable in order to create a linear programming model of the problem. A set of standard bags is available. D is the total number of deluxe bags. The two choices variable in the M&D chemical problem were A, number of gallons of product A, and B, number of gallons of product B, point S, and D. We're choosing the decision variable names. D is the total number of deluxe bags. The two choices variable in the M&D chemicals problem were A, number of gallons of product A, and B, numbers of gallons of product B. S and D were chosen as decision variables names. To make it easier to remember what this decision variable represent in problem, N, A, and B in the N, M, and D chemicals problem to make it easier remember what this decision variable represent into the problem. Although this method works well for linear program with a smaller number of the chosen variable. Dealing with a situation with high number of discussion variable can be difficult.
As for the last part, for a summary, as we formulated the lining programming models into two problems, the maximization problems we showed the graphical solution procedure and the computer solution with a brief interpretation. We developed about the general definition of the lining programming. The slack variable value can usually define or show of the amount of the unused resources, whereas the surplus value indicates the amount of some minimum requirement. Also, all the constraints had been written as equalities of the lining program has been written on its standard form. Infeasible or unbounded of the solution of lining program, obviously it is no optimal solution, or in other words, no problems to solve to be found. If the objective of the function is infinitely large for maximization problem, it's also the same for minimization for infinitely small. So that's for the whole summary for the chapter 2. This is once again Angelica Guiapal reporting. Thank you very much.